The reason why human babies are born so helpless and underdeveloped may seem quite paradoxical at first. It's because of their massive brains. Or rather, if they were any further along in their brain development at the time of their birth, they might be too big to fit through the birth canal at all. Throughout our evolutionary history, from great apes through bipedal hominin, ancient to modern humans, a confluence of factors has led to a situation in which human babies need to be born fully immature and to rely on their parents or caregivers for survival throughout the earliest period of their lives. As the first hominins branched away from the great ape lineage around 7 million years ago, they began walking upright as they explored new and open habitats. This bipedal way of getting around would require an evolutionary reconfiguration of our skeletons from those of our tree-dwelling ancestors in order to support an upright body firmly planted on the ground. These changes would include developing longer and more slender legs capable of gracefully walking and running, a reduction in the length of the arms, which are no longer required for brachiation or swinging from branches, nor for the occasional knuckle walking that is still common amongst our great ape cousins while they are down from the trees. Other changes included a flattening of the feet so that they would be more useful in walking or running on the ground than for grasping tree branches, and the development of more slender hands that are useful for carrying objects and fine manipulation of tools. Also, with an upright S-shaped spine with the skull perched directly on top, a new body posture is easier to carry around, rather than a curved C-shaped spine that attaches to the back of the skull, as is still seen in the chimpanzees, our closest related living relatives. However, the structural change to the human skeleton that would have the most profound effect on the human ability to birth large-brained babies would be in the anatomy of our pelvises. In other great apes, as well as our hominin ancestors, the pelvic basin is long and slender, but not robust enough to support the whole weight of an upper body that would be traveling around on 2 feet. As a consequence of habitual bipedalism, the hominin's pelvic basin would eventually evolve to become shorter and more bowl-shaped in order to carry the weight of our upper bodies. It would also become much more robust and inflexible in order to resist the stresses from the push and pull of leg bones walking and running. An inevitable effect of this pelvic readjustment was that the birthing canal in humans would become much smaller than in other great apes, leading to a scenario where birthing big-brained babies would likely be an impossibility. But we did become a big-brained species, so there must have been some evolutionary compromises taking place which allowed these mutually exclusive scenarios to somehow work together. One of the solutions that has taken hold in our species is to have much of the development of those massive brains take place outside of the womb and to give birth to babies that are not yet ready to be out in the world on their own at all. Yet, even with our birthing process being facilitated by pumping out underdeveloped young, it is still a heavily belabored event that would require a few other adaptations to help it along. One of these is the fact that, unlike in other mammals, the skull bones in human babies are not fused at the time of birth. This allows the baby's head to be squished and flattened on its way through the birth canal. Sometimes the squishing is so intense that the babies will have a cone-shaped head for the first few days of life, until those bony plates can move back and reposition themselves in a more rounded fashion around their brains. This is also why, for many months after birth, human babies have what are known as soft spots on the tops of their heads, regions in their skulls where the bony plates have gaps between them until, by around the age of 1.5 years old, they will fuse together permanently. In addition, by comparing to most other mammals, for which birthing is a private event, where females isolate themselves and give birth alone, in humans it is much more social. When we give birth, there are typically others present, whether in modern hospital settings or in ancient times as well. For humans, giving birth is a risky and challenging process, so it's important for us to have others around during labor to help out if needed. The tradition of having midwives assist in birthing of human babies is a direct response to the difficulties and risks inherent in pushing a big-headed baby through a tight and inflexible birth canal. In pre-industrial times, before cesarean section operations were an option, any complication during the process of birthing would likely have led to a dead baby, and, depending on the circumstances, the mother might very well have died during labor too, from hemorrhaging or sepsis, for example. These are strong evolutionary pressures that would favor babies having an underdeveloped brain at the time of birth in order to survive that literal bottlenecking event that could spell the difference between getting a good head start in life and an inevitable dead end for that family's line. As a consequence of all this, human babies are born with brains that are more immature and underdeveloped than any other mammal, with only around 30% of the brain volume that they will eventually have as adults. This means that most of our brain development occurs outside of the womb, and that leads to having very needy babies indeed. Over the course of the first 2 years of their lives, human babies will double their brain size during a period of unparalleled growth compared to any other time over their lifespan. But we know that brain tissue is the most expensive kind to grow and maintain, requiring 16 times more energy than building muscles. As they grow, human babies need more than twice the energy per unit of body weight than adults do. So how do our babies get all that energy and those nutrients required to fuel such a long and intense period of brain growth? The answer lies, firstly, by feeding on rich breast milk almost continuously during that time, and secondly, by relying on a backup system of body fat that they can consume when they're not suckling at their mother's breast. It may come as no surprise that human babies are plumper than those of other animals. In fact, the abundance of baby fat is an evolutionary adaptation to ensure that they always have a ready source of energy should they need it, and it can take up to 15% of their total body weight. With such a high demand on energy and nutrients for growth during the earliest phases of life, it should now become clear to see that growing a baby is an expensive proposition. Since females bear much of the brunt of reproductive inputs, from gestation during pregnancy to the constant feedings through lactation, we would expect to see adaptations in female body size and metabolism to accompany the evolution of larger-brained humans. And we do. Although indices of metabolic rate and body fat content are not available from the fossil record evidence, we do have indications that human females were adapting to these new energetic costs as recently as 1 million years ago. Looking at the skeletons of Homo erectus, we note that there had been a dramatic decrease in sexual dimorphism over the recently preceding evolutionary time. That is, female bodies were becoming closer in size and stature to those of their male counterparts. Although women are still, on average, somewhat smaller than men, those differences were much greater in our most recent hominin ancestors, the Australopithecines. The increase in female body size found in Homo erectus females suggests that it compensated for high energy and nutrient demands placed upon them that were not a factor in reproduction for their ancestors. Furthermore, the shape and size of the pelvis in Homo erectus was almost exactly like that of modern humans. So we can surmise that those females were faced with birthing challenges and that, like us, would have had to invest heavily in postnatal care and feedings for their big-brained offspring. Another piece of the evolutionary puzzle that may be inferred from this decrease in sexual dimorphism by the time Homo erectus came about is that the nature of the family bonds and relationships would have become more stable and monogamous than that of their and our ancestors, the Australopithecines. Extreme dimorphism is most often related to the sexual mating systems in which males may compete with one another to have access to many females for mating. Conversely, a decrease in size difference between the sexes is usually accompanied by more cooperative and monogamous pair bonding,
something that would be required if one of the parents had to devote 100% of their time to childcare so that the other partner could be counted upon to provide food and protection for their female partner and child.
We're starting to see a pattern emerge here, in which bipedalism, rich omnivorous diets, and social cooperation have created a synergy throughout human evolution from which larger, more caring, and more intelligent brains seems to be the natural inevitable outcome. However, another factor needs to be clearly seen here too. That none of this system would work without the commitment of caring parents who are willing to attend to the needs of their helpless young offspring. And anyone who's had children of their own will know how exhausting that can be. If it weren't for that love reward that we get, it can often seem overwhelming and not quite worth the trouble.
But there is a reward that keeps this system alive and kicking. Love is the key. Because of the complete and total dependence of human babies on their parents to act as present and stable providers, evolution has favored the development of one of the animal kingdom's strongest relationship bonds between parent and child. Psychologists call this the attachment relationship, and it is the key to ensuring that babies get all the love and attention that they need. But it also happens to form the foundation for the social relationships between adult humans that make them care for one another and cooperate with one another for their mutual greater good.
Human babies make their needs known by making a fuss, by crying loudly at pitches that most human adults find impossible to ignore or to endure. See what I mean? These sounds that babies and infants make cause adults to respond to those cries in an attempt to find peace again and to provide the child with what it needs, which is usually food and comforting and the occasional diaper change.
For the parent, this obligation is rewarded with soothing chemicals flowing through their bodies and brains, such as oxytocin or the love chemical, so that they feel an incredible bond with their child. It resets the relationship and renews the bond by erasing the hardship that the parent might just have experienced during their child's tantrum. For the babies, however, the care and support that is provided by the parent has a more profound effect on its own brain development. More specifically, the stable and loving relationship between a parent and its offspring helps to promote the growth and development of parts of the baby's brain that register and respond to loving and caring bonds between all humans, those related to the limbic system or emotional brain, and components of its prefrontal cortex. In fact, the proper growth and development of these crucial elements to human cognition and behavior are largely dependent on having experienced positive, loving, and stable relationships in the early years of their lives. A baby that is protected from danger, cuddled when needed, and fed when it is hungry by consistent and loving parents will be rewarded in their own brain with neurochemicals that are foundational to the feelings of being human.
The sense of safety and comfort that they receive will allow them to explore the world around them and to learn from their experiences without fear. The feelings of love and care that they receive will allow them to develop a trust in their own feelings and to rejoice in the presence of those around them. As we shall see, these most profoundly human behaviors and emotions are not only crucial to ensuring a safe and successful development throughout our most vulnerable period in all of our lives, they may be called upon later, when as adults we attempt to navigate life with our friends and partners so that we may act as a successful member of our community at large.